We're going to be asking a different kind of question today in relation to a function, and particularly its graph. So here we have an upside down parabola. Question you might not have ever thought about before, maybe you have, is what is the area between the curve, the parabola of this graph, and the x-axis? Okay, what is the area between the curve and the x-axis? This is where Riemann sums came into be. And we're going to talk about how to find that area, and later on in this class, how that's applicable to the real world. So this graph is f of x equals 1 minus x squared. The name of this lesson is Riemann sums left point. And we'll see why it's called left point here in just a second. So formally, here's the question we're asking. What is the total area between the curve of f of x equals 1 minus x squared and the x-axis on the interval -2 to 2? So if I just wanted to shade that in real quick, which I'm going to do right now, it would look something like this. Okay, so here's the area between the graph and the x-axis there, but then it kind of shifts, and now we have this area to deal with between the curve and the x-axis. So the graph is above the x-axis there. Then it changes back again in this area. So what if we wanted to find this total area? How would we do that? Well, there's a lot of different ways, and for the first way, we're just going to use left point Riemann sums. Here's what left point Riemann sums look like. You start with the leftmost point, and then if you read the question, it says from -2 to 2. So you start with the leftmost x value, and you draw a rectangle down until you hit the graph of the function. Okay. And then it depends on the spacing that you want to do. You know, your rectangles, the more rectangles you have, the more accurate it's going to be. In this case, we're going to choose the width of the rectangle to be half. Okay, so 1/2 or 0.5. And then once you determine that width, then you go back up and you draw and finish your rectangle. We can see now that when we draw these rectangles, they're not going to be a perfect representation of the area that we shaded here. They are going to be a guesstimate though. And like I said before, you know, the narrower the width of your rectangles are, the more accurate your Riemann sum will be. Now why are we doing this? Is because right now we don't really have a way of knowing the exact area between the graph of this function and the x-axis. We don't know what the exact area of these shaded regions are right here. So for right now, we're just going to use rectangles because, you know, rectangles have the simplest area formula, meaning width times height. So what is the area between the curve of the function, the x-axis, and the interval -2 to 2? Well, the first thing we're going to do is just do it the conceptual way. So let's talk about the area of this initial rectangle, which we're going to call A0. Well, the width is going to be the same for all of these rectangles. It's going to be 1/2. But what about the height? Well, the height is determined by the y value of this curve, which again is the formula for that. I'll put it up here is 1 minus x squared. And we'll just say y, even though it's the same as f of x. For example, if I wanted to figure out what this y value was, I would just plug in -2 into this function, and it would give you the y value. Now, the problem is, the height of a rectangle is never going to be negative, it's always going to be positive. So no matter what, we're going to put absolute value bars around our function to determine the height of this rectangle. So for the first initial area, it's going to be 1/2, it's going to be the width of that rectangle, times the absolute value of the y value. In this case, we're going to plug in -2 to figure out that y value. Now we can see on the graph it's going to be -3. So that means the height of this rectangle is going to be 3. And that's confirmed by this expression. It would be 1 minus 4, which is -3, but we have to take the absolute value of that to give the height of the rectangle, which is 3. If you take 1/2 times 3, you get 1.5, which is the area of this first rectangle. And again, what we're trying to do is guesstimate the area between the graph of this function and the x-axis, these three shaded regions right here. What do they add up to be? Now, I do want to point out that this question is asking about total area and not net area. When it says total area, what that means is we just consider all area positive. We don't consider the area under the x-axis negative. There are times when we will do that, and if that is the case, it will say net area, not total area. So we're going to go through and find the area of the next rectangles. Now this one right here, the height of this rectangle, we do not know, okay? We can see that it's unclear. It's somewhere between -1 and -1.5, which is why we need this formula. So to figure out the height of this, we will plug in -1.5 into our function to determine the height. And when we do that, you can just use a calculator, but it's going to be 1 minus whatever 1.5 squared is. Take the absolute value of that, multiply that by 1/2, and we will get the area of that second rectangle to be 0.625. Okay, so again, the area is always positive when we're talking about total area. To figure out the area of the next rectangle, we will do the same, follow the same pattern to be 1/2 times the height of the next rectangle. Now here's the problem. If we look at our next x value of -1, it will yield a rectangle with no height. So therefore the area of that rectangle is going to be 0. That happens sometimes with Riemann sums. You can begin to see why it's not the most accurate way of finding the area between a curve and the x-axis, especially if you have a small amount of rectangles. As I said before, if you increase the number of rectangles, the area is going to be more accurate. Now let's move to -1.5. The width of that's still going to be 1/2. The height is going to be determined by plugging in -0.5 into our formula. We find, once we crunch the numbers, we find the area of that rectangle to be 0.375. Okay, we're going to follow the same pattern. Plug in the next value of 0. We get the area of the next rectangle to be 0.5. Okay, so this one makes sense, right? You can see the y value is 1. 1 times 0.5, width times height is 0.5. And then the area of this rectangle is going to be, looks like about the same as that one. Let's take a look and see. And yes, you do get 0.375 for that one. Then when you run into 1, right here, you see that you yield another rectangle of 0 because the height is 0. Now remember, this is left point. Why is it called left point? Because the y value of the rectangle, the height of that rectangle, is determined by the left point. You can see that as you draw these rectangles, every y value is determined by the left point, not the right point. We'll talk about right point in the next lesson. And then the last rectangle will be determined by the left point of that rectangle, so 1.5. And I did not draw that one for some reason. So let's go ahead and do that in 1 second. Actually, you can go ahead and watch me draw that right now. So that would be determined by going down until we hit the graph, and then going over, coming back up like that. So it's going to look like that. So the area of this rectangle, again, the width would be 0.5. The height would be determined by plugging in 1.5 into the function, and we get 0.625, which was the same exact area as this rectangle over here. And that's because there's some symmetry going on. So the question is, if we add up all of these rectangles, that's going to be a very rough approximation of that initial area we were trying to figure out. So if we add up all of these areas of all of our individual rectangles, which we're doing right here, we get 4. What that basically means is we've estimated that the area of all of these is 4. Now, what are your units? Well, it depends on what x and y are. It depends on the units for that. So let's say we're talking about feet for x and y. Let's say every tick mark here is a foot. Then the area would be in square feet. So this would be a total area of 4 square feet. Okay? Or you can talk about meters or whatever units you're using. So the real question is that an accurate representation? Well, I don't know right now, but eventually we will learn, how accurate is it? What's the margin of error? But I do want to teach you some steps for using left point Riemann sums, because you don't always have time to draw the function. I do encourage it if you can, but you don't always have time. There is an analytical way of doing it every time that works every time, so we're going to go over that. So the first step you're going to do when doing Riemann sums is to determine the length of the interval, so the horizontal width. This problem said to find the area from -2 to 2, so I'm just going to draw a line from -2 to 2, and the question is, what's the width of that line? Well, all you have to do basically is take your rightmost value and subtract your leftmost, and you get 4. So that's your first step, is just to determine how long is the interval you're dealing with. It's 4 units long, 4 feet, 4 meters, whatever. The next thing you're going to do is to determine the number of rectangles. Now, this is actually up to you a lot of times when you're estimating. However, if you're taking a test, the test will be clear about how many rectangles to use. Like I said before, the more rectangles you use, the closer you're going to get to that and estimating what this total area is. The more the better. Now, I used intervals of, well, I actually determined, let's see, 1, 2, 3, 4, 5, 6, 7, that I wanted to use at 8 rectangles. You could have done 10, but in that case, you know, the width of the rectangle would be 4 divided by 10, which is 0.4, and so it just gets kind of weird that way. One that's easy for most people is you could just, you know, always make the width of your rectangle 1. In this case, you'd have 4 rectangles that would be wider. But like I said, usually it's going to be clear for directions. So in this case, I chose 8 because if I do 4 divided by 8, the width of each rectangle is going to be 0.5. Which leads us to talk about this. If the problem does not stipulate the number of rectangles, try to choose a number that is convenient and practical, yet accurate. Sure, 4 rectangles in this case would be practical, but let's go with 8. We can calculate rectangles of width 0.5 relatively easily. So you just kind of look at the width of your interval, in this case 4, and you go from there. You know, again, if you do 4 over 8, that's 0.5, which is pretty easy to work with, even though it's a decimal. This leads us to the next step, which is to determine the width of the rectangles. All you have to do is take your interval length and divide by your number of rectangles. Steps 2 and 3 kind of go hand in hand. You know, like for example, you wouldn't want to choose 9 here, right? If you have an interval length of 4 and you divide it into 9 rectangles, you're going to get some weird decimal back for the width of each rectangle. So try to make it, you know, you can make it 0.25, right? And in that case, you'd have 16 rectangles and you're going to get a more accurate area. And so just try to make it to where it comes out semi-even. So in this case, I chose 8. 4 divided by 8 is going to give me the rectangle width of 0.5 each. Notice I keep going back to the picture, and that's because when I first learned this, I have to be honest, I was really confused. To me, what really helped was drawing it and kind of visualizing each rectangle, which is what we're doing here. So now we get a width of 0.5 for each rectangle. And again, you don't have to draw the picture if you follow these steps correctly. You'll eventually get to the point where you just analytically do these steps without actually having to draw the graph. But for now, we're definitely going to look at the graph for conceptual reasons. Now we're going to determine the x values of each rectangle. It's all the x values except for the last one. Now, why is it all the x values except for the last one? That's because we're doing left point. So we're going to start at -2, then we're going to go -1.5, -1, -0.50, 0.51, and 1.5. I always call my initial x value x naught, and then we go all the way up to x7. Since there's 8 total rectangles, it makes sense that it goes from 0 to 7. That's 8. We do not include 2.0 because we are using the left point method. So you can see what this looks like. You always start with the leftmost x value for left point. Now I'll even go ahead and notate up here. This is left point. And you go all the way over until not the last one, but the next to last one. If you were using right point, it would look like this. You would skip the first point and you'd use all the other ones up until the end. Okay. So just pointing that out for the left point. The left point. Your rectangles are determined by the leftmost points. Okay, step 4 is to determine the height of each rectangle, as we just did. And so if you've already got these x values written out, to find the height, you just take the absolute value of the y value for each of these using your function, which is 1 minus x squared. So we are going to do that in this slide. Just plug in all the x values in the function and take the absolute value, which will give you the height. Again, we're finding the total area right now. We're not finding net area. If we're finding net area, we would not use these absolute value bars. So we're basically just plugging in our 8 left point x values to figure out our y values, and we're taking the absolute value to give you the height of these rectangles. Now you might be thinking, well, what about the width? Well, if you think about it, all of these have the same exact width. So that width is a GCF. It's a factor they all have in common. So rather than multiplying all of these by the width every time, why not just add up all the heights and multiply that by the width? Because you're ultimately just pulling that out. So that's what we're going to do. Step 6, just add up all the heights of the rectangles. We get 8, and then step 7 is to multiply them by the width of each rectangle. So 8 times 1/2 gives you 4, which is the same number we got before, and that gives you a rough estimate of this area right here. Okay, we are going to guess that it's 4 based on these rectangles we drew using left point. Again, I forgot to draw my last one here. Draw it again. And before I finish, I just want to show you kind of what pulling that GCF looks like. So when we first did this, we multiplied each height by the width. But we could just pull that 1/2 out, add up all the heights, and then multiply our answer by 1/2, which is exactly what we did this way. And it's just more practical. Like it's just easier. It saves you a lot more time. You're not multiplying by 1/2 every time, which is why we did step 7. So that's it for left Riemann sums. Okay, you're not going to fully understand this right now until we go through right point, midpoint, and some other methods, and then you'll really start to see, okay, yeah, I don't have to draw the picture every time. I can just do these 7 simple steps, and it's going to give me a good approximation of the area between the curve and the x-axis. That's it for left point Riemann sums. If you have any other questions about this, let me know.